of the to the topic of the conference. Which is of course factorization, right? So I hope after scratching my head, I think there may be a factorization problem here, but for now it is a kind of certainly a canonical problem in diffraction, certainly unsolved. Who knows? Maybe I need to learn more of Wiener-Hopf type techniques to advance it further, right? So here is the outline. In fact, the problem has quite a bit of a history, several decades by now, and first it was formulated and stated mathematically as a boundary value problem for appropriate PDE by Prof in 1970s. And a point to make is here, I will try as a motivation, right, before we go to the technicality and to the actual well-posed mathematical problem for a non-separable PDE, by the way, that it's really important, canonical, arguably even fundamental, right? Arguably it is as fundamental as RE-ODE is as a model for connecting oscillations and exponential decay, right? Light and shadow, right? On a similar token, arguably it is a canonical model connecting two worlds, PDE rather than ODE, connecting model to scattered behavior or discrete patterns with a discrete spectrum to patterns with a continuum spectrum, right? That's kind of philosophical point. And as I said, mathematically, it's really, here is a missing tool, right? How to connect these two asymptotic, completely different asymptotic regimes at two ends, and ultimately to find the map connecting these two asymptotics, and ultimately this may require a hybrid of asymptotic and numerical tools, a combination of the two, and there is a reason advances in this direction, but who knows, there are some signs that there may be a factorization problem hidden behind, and that I will try to tell a bit to sort of explain this part. Oh, sorry. Right. So here is this incomplete list of references, as I said, starting from Popov, 1970s, early 80s, and in fact that was my part of my nearly failed PhD, right? Since little consolation, the problem is still largely unsolved. And then after that, I switched to other problems, now coming back to some enhanced life experience. And one recent publication, in fact, of this year is with Dave Hewitt, my young colleague at UCL, John Kindon in Oxford, publication in wave motion. In fact, this uses complex analysis tools, and as I announced, there may be some factorization problem hidden behind, but that's also following some recent ideas of Kazakov as a kind of another representative of St. Petersburg, St. Petersburg school there. Okay, so what the problem is anyway? It looks like physically, right? Physically looks like a rather esoteric and specific problem, but it is important, even fundamental, arguably, right? There is we study, we are interested in particular solutions to the Helmholtz equations at high frequencies, right? Which may propagate along concave part of the boundary, and they are of so-called whispering gallery type, right? They happily propagate that until the concavity switches to convexity, right? What happens next? No one really knows, right? So why fundamental? Because again, before we go to maths and ultimately theorems, in wave propagation there are two completely different regimes, right? If you That's how I explain it to myself and to others. So interior problems and exterior problems, right? If you draw a boundary, right, then in the interior you have eigenfunctions and eigenvalues, right? The waves oscillate forever, right? Model behavior, right? In exterior problem, it is opposite, right? It is a scattered behavior. Nothing oscillates forever. Everything earlier or later goes away to the infinity, right? These two don't interact. But at high frequencies, things tend to localize, right? If you have part of the boundary which is not globally but locally concave, right? Then you have solutions which locally behave like model solutions. And the same for the convex parts of the boundary. And if you have a transition, inflection is a model for transition, right, of the model behavior to the scattered behavior. Something radically changes in the neighborhood of this point. Mathematically, here we have an operator with a discrete spectrum. Here we have an operator with a continuous spectrum, right? Here we have something which locally connects discrete patterns to continuum, right? That's perhaps a bit of hand-waving motivation. And this shows up at all levels, including for when trying proving, analyzing appropriate PDEs and showing the theorem. Now, how the problem is formulated mathematically, right? So you do this kind of asymptotic analysis, and it is known that there are special patterns near concave part of the boundary of so-called the whispering gallery type solutions, right? They are visualized as naively some limits of geometrical optics when you bounce like this billiard race, which bounce the boundary, reflect, and you have a small angle of reflection. And if the angle is really small, this sort of wave patterns tend to concentrate in a small neighborhood of the boundary, right? And the curvature matters, right? So in fact, here are some formula. I don't think we need to go to the detail. So if we introduce this a normal system of coordinates, right? N normal to the boundary, and S is arc length along the boundary, right? And then it is known that there are particular asymptotic solutions to Helmholtz equation. Say, take Dirichlet boundary condition. So they tend to oscillate along the boundary, take out this oscillatory thing, and then they tend to concentrate in a small boundary layer, right, near the boundary. That there is a kind of boundary layer machinery for that introduced stretched coordinates, and then it appears that Airy function is in fact the sort of Airy ODE pops out from there, and it describes kind of these oscillations in a small layer, right? And then curvature enters everywhere. Everything falls down, breaks down if the curvature degenerates, right? If you start getting close to the inflection point, then no more whispering gallery solution. So Popov studied. So what happens in the neighborhood of the inflection point? Again, how to guess what is the right model and the right boundary value problem. You take a magnifying glass, a microscope, you look inside, and then you sort of see half space, right, in your inner problem. Then you need to be clever to find the right stretching. It appears that K is a large parameter, right, high frequency, a large wave number. The exponents are here 3/5 for the normal parts and 1/5 for the tangential, right? And after similar sort of taking a oscillatory part there, one ends up with PDE, right? It looks like Schrödinger equation, Schrödinger type equation. See, there is no time, right? But it's officially this tangential component serves after the stretching. It resembles, it's called by T, right? By analogy, right? So it's sort of becomes causal problem, right? In diffraction, in fact, it is known by due to Fokal and Tovich. I think it's historical, terminological kind of confusion. It's called parabolic equation method, right? Even though it's not parabolic equations, Schrödinger type. equation. So this little I matters there. It's more of kind of hyperbolic type, but causal equation. Okay, and then the boundary condition, Dirichlet. So we have this PDE in let's remember that. So that's all we need to know. Ultimately, t and x half space. What could be there, right? A PDE u x plus x t u equals 0 and Dirichlet boundary condition, right? Because of this little thing, not possible to separate, right? No exact solution. This is a source of a problem. Nevertheless, if you do all this asymptotic analysis, there is well understood this whispering gallery mode coming from the left, right? It appears that it is separable asymptotically, right? After you have stretched your coordinates, you need to go to the outer world t. When t goes to minus infinity, you should expect to match your thought solution to what is inherited from the incoming whispering gallery mode, right? And the Popov did a lot of things, including this one. So it's, and in the end, this is a well-posed boundary value problem, right? PDE, boundary condition, and asymptotic condition at minus infinity, right? So the solution, the thought solution must converge to this difference between the two and L2 norm, right? Converge to 0. It's all well-posed problems. So in fact, you can construct a full asymptotic expansion at minus infinity. This guy will be just the first term in full asymptotic expansion, right? Now, however, that's what. How can I solve this problem? No way, right? It's not separable PDE. So, however, if you naively froze t, took t large negative, right? If it were a constant, you could scale it out, right? And that would have been model operator for the separable Schrödinger equation with the discrete spectrum, right? On the left end, when t goes to minus infinity, right? You would have here plus, I think, right? And similarly, on the other end, sort of you can say that the equation is asymptotically separable. And here is, in fact, yes, whispering gallery asymptotic pattern at minus infinity end and scattering continuum spectrum pattern on the other end, and the solution somehow matches the two. And here the analogy with Airy function comes quite close. Suppose if you are first or second year undergrad, you have learned elementary functions, you haven't yet learned special functions, right? You try integrating it, you could not, right? So sine, cosine, so you need to introduce a new special function, right? But it is asymptotically, if you naively froze x, made it large negative, you will have what, two oscillating solutions, sine, cosine, and if large positive, exponentially growing and decaying, right? Throw in growing solution, decay, and unphysical decay. And so the question is, what? So how this asymptotics at one end connects to decay at the other end, right? So here, all you need to know is kind of, and the acoustic is, again, it's philosophical, right? Acoustic is just one of visualizations for something even more fundamental, right? It's a model connecting oscillatory behavior to non-oscillatory light and darkness. All right, and similarly for this ODE, if I were naively freezing t negative, in fact, I will recover incoming whispering gallery mode. If I naively froze it as a large positive, I will actually recover model of grazing diffraction, which is also well understood that it is a separable PDE but operator with a continuous spectrum, right, rather than discrete, right? Again and again, the key question is how to connect those two regimes, right? This is again, maybe not all the technical detail is important here, so you can separate variables. The solution is here, it's continuous spectrum. Solution is integral, right, over lambda spectral parameter. This guy satisfies the boundary condition. It appears that the incoming sort of incident wave is accounted by this term. It's the Airy function, and this corresponds to outgoing solutions, all separable, and all the necessary information, including the subtleties of formation of the shadow and creeping waves, right, and exponential decay here, and the subtle transition. They're all hidden in asymptotic analysis of this exact solution. Already complicated enough, right? Now it becomes worse. Now this naive intuition of freezing the parameter, if it were constant, right? In fact, I could have taken it out. I could try doing both ends, right? If t were constant, I can get off it just introducing new variable as t1/3, right? Then it splits evenly there. Since it is not constant, there is a perturbation, right? But the perturbation is perceived small, and it appears that kind of recovers that fact that, and then you need to be careful. It's indeed small at one end and not quite small. Where are we now? When I have plus at the discrete spectrum, everything is like whispering gallery wave tends to sit near the boundary. Psi, which is stretch x, is not too large. Tau in the denominator is large negative. That's a really small perturbation. That's all fine. At the other end, things tend to get away from the boundary, and here you need to be a bit more careful with this perturbation analysis. So in fact, it has to be supplemented by something else, right? So what is known? Quite a few things are known. Maybe I will skip some details. Time runs fast. This is a well-posed problem, right? There exists unique solution in appropriate functional spaces. Ultimately, this is a classical solution, infinitely smooth, right? And it decays. So it is. You remember that. This physical intuition would help if we have this incoming whispering gallery mode, right? If it is visualized by this multiple nearly tangent reflections, then when curvature changes, that this guy loses contact with the boundary, right? And what you should expect, there is some kind of searchlight, right? The beam, right? Some concentrated solution near the limit rate, right? Naive intuition, the searchlight would be expected everywhere, and then after all this change of variables, this searchlight becomes a bit weird cubic parabola. But everything above this, there is a whispering gallery modes there. If you go far away, you are kind of in the shadow. Solution is small there, and then you expect it to be small again, and there is now some ultimately creeping waves, right? You would expect appearing here, and that's quite a long way to go. So we did show, actually my first paper ever during my PhD studies. So you can really construct formal asymptotics formally match with whispering gallery and show that solution is indeed small formally above the limit ray here, and you can rigorously prove, and that's like formal matching. Maybe you can rigorously prove that it decays at least extra polynomially, right? Formal asymptotic is exponentially small. This decay is polynomial, right? Then you can try doing perturbation analysis at the other end, right? At the continuous spectrum end, and it doesn't quite work, right? For this fact that psi squared is you cannot neglect it anymore, right? Since the solution tends to beam around, right? It's not anymore concentrated near the boundary, and so here psi is the stretched x becomes large. So, but you can nevertheless do some formal asymptotics. It will be helpful in the end because there will be some more complicated pattern on the other side, and then it is a kind of solution has to be decomposed into eigenfunctions of generalized eigenfunctions, right, of continuous spectrum. That's also reasonably well understood, right? Without perturbation, you have asymptotic separation of variables, and that's kind of your spectral density. And you expect, if it were suddenly stabilizing for large tau, which would be morally equivalent to this diminishing role of the perturbation, then you could make ends meet, and you could even get ultimately this amplitudes for the searchlight, and even if you are lucky, even by analytic continuation and residues as a result of this poles of analytic continuation to get creeping wave contributions, right? So in reality it's a bit more subtle, but here again this searchlight thing, you can sort of make it working. So in what happens in reality after the inflection, the wave pattern actually sort of forgets about the boundary, right? It becomes too far below, and it more or less kind of free propagation, like in a free space. And it appears that, again, back in that paper with Babbage, part of my PhD, in an attempt to do matching of asymptotics, we recovered that the expected ansatz for this searchlight has a particular form, which there is some mysterious transformation of the free Schrödinger equation, and it appears to be up to another change of variables. It is one more free Schrödinger equation. So in fact, my colleague Ilya Kamonsky, who is widely educated, spotted that curiously this kind of is known in the literature, recent literature, as pseudo-conformal symmetry of free Schrödinger equation, and even famous Terry Tao had an online note, right, on this in 2013, right, more recently. So and it appears that these guys after this transformation, this solution of this new equation, and will provide amplitudes of the searchlight. Perhaps details could be skipped here. One perhaps acknowledgement is necessary that in the St. Petersburg school, Vladimir Buslaev, right, is another sort of authority, who sadly passed away not long ago, and he developed this kind of a wave operator theory with a non-standard version of how the formal asymptotics translate into rigorous analysis, and in this case for this particular pattern of the ansatz. And it looks like you can make ends meeting here. So one more thing here, time runs fast, is that you can do perturbation analysis at both ends. The problem remains, right, how to connect them, and in the absence of exact explicit solution. Luckily here, and this is a tool both to push a little bit further asymptotic analysis, but ultimately perhaps to do numerics, right, that the problems luckily allows a boundary integral equation formulation, right? So if you forget about the boundary, right, and consider Green's function in the whole space, fundamental solution, luckily you can, it is, if there was no this guy, right, this is more or less kind of standard version, almost from the textbook, Schrödinger equation similar to Heat equation, right? Complexified guy. There is this exponential, becomes oscillatory rather than decaying, and this prefactor -1/2. And this is a kind of small perturbation which adds more regular terms on the top of that. And then you do this usual Green's representation analysis, and you end up with tractable numerically and analytically as well, integral equation. Moreover, it is of Volterra type, and it looks quite similar to what our chairman recently studied with Korolkov, right? It's like in a similar problem, it can be done solved quite efficiently numerically. Okay, here is the details for those who care. The kernel is actually not that bad, right? It is crazily oscillatory, but it's finite. The domain is infinite. However, you can regularize it because you know asymptotics of the third solution at minus infinity end, right? If you subtract as many terms as you wish, the rest will decay as fast as you wish, and that essentially becomes, after change of variables, classical Volterra equation with uniform convergence of Neumann series and so on, and some possibility to do something about further analysis. Now, in the absence of time, now my justification for presence at this workshop, if there is any. Could there be any factor? The problem is unsolved, right? Question for you, for the audience. Can factorization techniques be relevant here? There are some indications that they may be, and some details are in fact found in that paper in Wave Motion 2019. There is a link, there is a reference in the abstract online. So if you try looking for particular solutions to the Helmholtz equation, again, even like working in polar coordinates from the very beginning, again the same stretchings, and then you get equation, free Schrödinger equation, but a curved boundary, right? Can you find any solutions which would mimic all these expected patterns, right? Incoming whispering gallery wave, the searchlight, possibly creeping waves, and so on. And it appears, again, driven by analogy with this Fock-Leontovich gradient diffraction problem. There are particular patterns. Now it is a quintic order exponential integral, some unknown prefactors, and the choice of integration contour gamma, right? Appropriate choice. Now again, skipping the details just to give a flavor. Since we have quintic contour, then the ends must be sitting in exponentially decaying paths. There is plenty of choice of these sectors. Right? Similar to Airy function has 3 sectors. This guy has about 5. And then you can work out what sort of the fifth order term. There is about 4 saddles, right? And then you can see all this saddle transformation and coalescence of saddles into this caustic type effects near the cubic parabola precisely. And it appears that out of all those guys, there is only one combination, one contour, which is consistent with incoming whispering gallery mode and nothing else, right? And there is only one other guy which is consistent with no incoming components whatsoever, only outgoing components, right? So if I denote P minus and P plus, these 2 guys, then to capture incoming whispering gallery mode, I do need some function with certain analytic properties with some prescribed asymptotic behavior, and the other guy also has some inherited analytic properties from all this asymptotic information available to us, and taken together, crucially, they have to satisfy appropriate boundary conditions, right? Some details are there. In fact, some my Dave Hewitt and Andrew Gibbs, my young colleagues, they did some calculations supporting this, right? It's kind of one particular choice of the contour consistent with like whispering gallery mode, and then there are other guys, but they're missing expected pattern at this end, and the other choice is also does recover what we expect there, like whispering, creeping wave type behavior, and then challenges, since like there are indications that there is a factorization problem hidden behind, and sort of would be interesting to see if this sort of ideas may help advancing it further, maybe ultimately even solving more exactly, or sort of understanding better what exactly happens. And here is summary. So that's again important problem, fundamental in some respects. Then unseparable PDE, no explicit, no exact solution easily available. At least some perturbation analysis can still be done, and the question is how to match to asymptotic regimes, and ultimately maybe a way forward is to do hybrid of asymptotic numerics, and there is a very nice boundary integral equation here, and an interesting integral open problem. Could factorization methods be helpful with some indication that they may be relevant? Yeah, I think that's all. Thank you very much.
Thank you very much. Anybody has any questions?
Is Popov's equation known to be a correct description, so that the unsolved bit is solving Popov, or is there an unsolved bit getting to Popov, so you don't know that Popov is really right?
No, Popov is right, but the question is, because Popov has done many things. It's first thing he has done, right? He has reformulated the problem in a problem, right? Is the boundary value problem for this PDE, right?
To be the correct asymptotic description in a problem.
Yes, and this is a well-posed problem. Even arguably, you can say it's similar by way of analogy. Is IRE equation correct model for caustics, right? You can ask. Well, of course it is, but someone will tell, even if it is not, it in its own, it's already interesting enough because it already displays connection, right? Yeah. On the same token, that's believed to be correct model. But if it, even separately from this model in its own already has this key features. It has two. It is asymptotically separable to discrete pattern on one end, to continuum pattern on the other end, and big question is, it's a model for connecting the two worlds, right? And inflection is just one particular visualization, right, of something even more fundamental, like caustic is just visualization of something even more fundamental, right, connecting oscillatory and non-oscillatory worlds. Here connected model and scattered worlds, right? And that's all sitting in this model. You can forget about even motivation, inflection, and study this in its own. Very simple, right? What could be the PDE boundary condition, and it's not a big deal to find the symptotic. So, but solvable or not? And if so, can you connect the two asymptotics?
Thank you very much. Anybody? Some other questions?
Just not a question, but a light-hearted comment. I mean, the picture that you have with sectors,
right?
One, etc. So this picture is next to an integral when you have an odd or order polynomial in the exponential. This looks like stuff from Thanasis Focus or Beatrice Peloni paper. So it should be a really good problem there. Just visual.
Yeah, well, sure enough, except when was their paper, right? It's all kind of goes back to...
The answer to the last question in the conclusion is yes.
Yeah.
Sure.
No, actually, truth is that both Thanasis not yet emailed to me from Greece yesterday, right? I'm safe, I suppose. But and Beatrice as well. For both of them, I said, yeah, they're great methods. Some people are enthusiastic about their methods, others may be a bit skeptical. This is a real test, right? Can you solve this boundary value problem? Still, please, I'm still waiting to hear back from you, Doctor.
So, if there are no other questions, let us thank our last speaker and let us